All right, now titrations. This is what we are trying to accomplish here. Is how we can take this workhorse of chemistry and figure out what to do with it. So, since only a very small percentage of acids and bases are considered strong, the incredibly vast majority of acids and bases are weak. So we have to counter how we take that into consideration. So we're still going to deal with weak or strong acids and bases as titrates, because that gives us something that we can predict as far as concentration or moles of hydrogen or hydroxide, depending on what we're dealing with. But since the weak acids and bases act differently than the strong acids and bases, we're going to take a look at how that changes the calculations and the graph of the overall titration. Okay? So, we'll start off with weak acid, strong base. Again, we'll go back to our chart. Now, I said I was going to send you one of these, but I think you can just make your own chart on a piece of paper for this. I kept trying to come up with something that would work, and I had issues with it, and I'm old and I can't figure out issues until I sit down and work on it for like a very long time. And since this is not a year to do that, I will probably have to do that next year. But regardless, this is how we're going to start. Now, one significant difference right off the bat. You notice that I put a number with a big space underneath it. The moles of excess and the concentration of excess is going to require double lines or double values in each box, except for this one right here. That's the only time that won't happen. But the rest will be until we get to stage 4. Now this is the stage 1 of the titrations, and we're going to break that down bit by bit here so we can see what's going on. But this is what we are given. We are given that the concentration of a solution, let me bring it up over here. We are going to take, according to the example here, we're going to take nitric or nitrous acid, not nitric, nitrous acid, which is a weak acid. We're going to titrate it with sodium hydroxide. But before the reaction even starts, we have all acid, no base. Now, in the strong acid, strong base titration, we just took the negative log of the hydrogen ion, of the acid concentration, because that would be the same as the hydrogen ion concentration for those 6 strong acids. We can't do that here because it doesn't break down 100%. This double arrow tells us we got issues. And the issues means that we're going to have to do a quad form for a weak acid. Okay? So, let's go ahead and take a look at this. We have 0.5 moles per liter of the concentration of the weak acid. I'm going to lose X here, gain X here, gain X here. So that's our mini ice. That gives us X squared over 0.5 minus X equals 4.5 times 10 to the negative 4. Quad form that, well, we put this in quadratic equational form, which would give us negative X squared, negative 4.5, or minus 4.5 times 10 to the negative 4X, plus 2.25 times 10 to the negative 4 equals 0. Plug that into quad form, and we get 0.0148 moles per liter for our X, which is our hydrogen ion concentration. So the pH is very easily found out by taking 1.8 negative log of that, which is 1.3. So we have 2 values to put in our chart on the right-hand side, 0.0148 for our concentration, right here. And I'm going to put just H positive because it's not the weak acid anymore. It's the actual hydrogen ion concentration that helps us determine what the pH is going to be. And then when we took the negative log of that, we said that that is going to be 1.83. And that is going to be 1.83 right here. Now you notice there would not be a double answer for pH, because the pH is going to be based upon either the hydrogen or the hydroxide concentration that we end up with from the bottom of the concentration of the excess. Now, one thing we haven't done is put in the number of moles for this. So I'm multiplying each of these by 0.5. It's 0.5 moles per liter times the volume. So this is going to be 0.005, 0.01, 0.015, 0.02, 0.025, and 0.03. Okay, so now, so that's stage one right there. In stage one, we're going to be using quad form of the Ka. So that's going to be the basic process for all stage one. Now, you take a look, had this been a strong acid with a concentration of 0.5, this would have been 0.030. This is much higher. So there's a big difference between the weak acid and strong acid. The weak acid titration starts at a higher level. Okay? Stage two. Now in stage two, this is again defined the same way. We have the moles of the weak acid is greater than the moles of the strong base that's titrating. What is different here is that we're going to get a buffer. Now why? Well, in the strong acid, strong base titration, we eliminated all of the base and had nothing but strong acid left over. And because it was strong acid, it was really easy to figure out the pH. In this scenario right here, this is the reaction that's taking place. Yes, it is a kind of a neutralization reaction, but it's not really, because you have to have identical strengths of acid, meaning and bases, meaning you should have both strong acid, strong base to get a full neutralized substance, meaning pH 7. We're not going to end up with pH 7 for our complete neutralization of the two ions that are being added together, or the two components, acid and base. So let's see what happens here. Well, the strong base here for the first part of stage two is 0.005 moles. So we're going to put 0.005 moles here. Now at this point, we're going to say that we don't have any conjugate yet. It's 0. Now, just like the strong acid, strong base titration, this is the smaller of the two quantities. So that weak, or that strong base, gets completely eaten up. And it's going to subtract 0.005 to both components of the left-hand side of the reaction, and it's going to add 0.005 moles of the new weak base, which is the conjugate of the weak acid. Now, how do we know they're conjugates? Because these are virtually the same compound, except you have a hydrogen on here and you don't here. In fact, this sodium, when dissolved in water, because sodium is a group 1 metal, doesn't stay with it. And we're really only looking at the NO2 negative ion. So the difference between these two is the lack of the proton or the hydrogen here, as defined by either Bronsted-Lowry or Arrhenius. So this is now completely gone. We subtract this, we get 0.015 moles of the weak acid. And over here, we have 0.005 moles of the weak base. Well, titrations creating a solution of a weak acid and base has now created a buffer, as we said. Now, what is a buffer again? A buffer is a combination of a weak acid and conjugate base mixed together. And that's what we have now. So we have to put both these into the moles of excess. So the moles of excess now, I'm going to put this in red, 0.015 of the weak acid and 0.005 of the weak base. Now for the concentrations, we divide both of them by 0.05 and we get 0.3 moles per liter of the weak acid, and we get 1 moles of the weak base. Moles per liter, not moles, moles per liter. We can now plug that into Henderson-Hasselbalch. So, Henderson-Hasselbalch, which states that pH is equal to pKa plus the log of the concentration of your base over the concentration of your mass. So, and P, remember, means negative log of whatever. So this is the negative log of the Ka. Well, the Ka, we said, over here, is 4.5 times 10 to the negative 4. Plus the log. Now the concentration of the base, we didn't put there, it's in the chart. Concentration of the base is 0.1, the concentration of the acid is 0.3. So we put those numbers in there. Okay, and that is going to give us our pH. And so we take the negative log of 4.5 E negative 4, close parenthesis, plus the log of 0.1 over 0.3, and I get 2.87. Okay, now that's actually kind of interesting, but let's put that up there before. Keep going the wrong way. What else is new, right? 2.87. Now, this exemplifies a second difference between the strong acid, strong base titration and the weak acid, strong base titration, in that the strong acid, strong base titration had a very slow incremental rise. Remember, it was very logarithmic. 2.87, big jump, a jump of 1 right off the bat for the first 10 milliliters of solution that we added. That's a huge difference. Now it's going to tail off after that, but that big leap is a major difference. So it starts higher on the weak acid strong base, and it jumps initially on the weak acid strong base.